What is stress in materials, not people? Stress in a material is a result of applied load, and engineering stress is the applied load divided by the cross-sectional area of the part in question. The force or applied loads could be the result of a weight at the end of a line or something on top of a column. For example, when I sit in this chair, my weight applies a load to the chair and thus stress in the support elements of the chair. Stress comes in many types, and in this video I'm going to talk about 4. Axial stress, shear stress, bending stress, and torsional stress. The other types of stress are either derived from those stresses or are applied to specific scenarios such as pressurized vessels. Start by looking at axial stress. If I have a cylindrical beam with a force that is aligned with the main axis, we're going to have axial stress. And that stress, denoted with sigma, A, is going to be that force over the cross-sectional area. In this case, if it's a cylinder, it would be pi r squared. The next stress I want to look at is shear stress. If we look at that same cylindrical beam that's fixed at the bottom, it would be a force that is perpendicular to the main axis. We denote shear stress with tau, and sometimes we'll see a force that results in shear denoted with the letter V. So in this case, it's V over the cross-sectional area. Same cross-sectional area. In the case of a cylinder, it would be pi r squared. Next, we'll look at bending stress, which is a little bit more complicated because we have to look at the moment of inertia. So if we have that same beam fixed at the bottom, and we have a force that is, in this case, perpendicular to the axis, we know it's going to create, pick a different color here really quick, a bend in this cylindrical beam to be where the red mark is. We also, so to find this, we first need to find the moment, which would be this force, we'll call it F, divided by this height to the fixed point. That will be a reaction moment. So that moment is going to be this force times h. And then bending stress is going to equal the opposite, this negative sign is important, the moment times y, which is the distance from the center. So if we look at this cross section as a circle, y would be however far out from the center or from the neutral axis we are looking at this stress. So max stress in this case would probably occur right at the edges. In that case, we would use C. Anyways, moment times y divided by the moment of inertia I. The moment of inertia is different for each cross-sectional area, and it can be looked up or derived, often in textbooks or the internet. So the max bending stress would be this C over I. And the negative sign helps us know whether we're dealing with compression or tension. If we look at the red outline that I've drawn here, the left side would be in tension because it's being pulled, but the right side would be in compression. It's, being tight, it's being pushed together. We tend to call tension stress positive and compression stress negative. So that just helps us know, are we dealing with tension or compression, this negative sign here. Alright, the next stress we want to look at is going to be torsional stress. Again, we're going to look at this same beam, but instead of applying a linear force, imagine we're going to grab the top of the beam and we're going to twist it like that. It's going to be a moment. So torsion is just the twistful force, the torsion, and we can call this T. And it's a type of shear stress, so we're going to note it with tau. And that is going to be this T times rho, but it's the distance from the center, same as y in the previous equation. On a circular cross-section, this distance would be rho. But we're going to divide by the polar moment of inertia, J. And again, the pull moment of inertia will change from cross-section to cross-section, and it's important to look that up before starting your problem. So these are 4 types of stresses: axial, shear, bending, and torsional, that we're going to look at in this video.